Hi there. Before we get started building our CPU, I thought it would be good to go through a little exercise showing us what a computer can do for you and what it can't do for you. Now, a computer is a machine that will run algorithms. The questions are that can we create an algorithm for every mathematical question that we want, and is there a master algorithm that we could write that could potentially solve all mathematical problems? So that's what we're going to look at over the next two videos. Now, in these videos I've actually taken the liberty of already writing some of it out just to save a bit of time. Okay, so one particular algorithm that we could look at is finding the highest common factor between two numbers. So if we take our numbers 3, 6, 5, 4 and 1, 3, 6, 5. Now we can find the highest common factor between those by dividing the larger number by the smaller number and taking a remainder. So if we do that there, we get a remainder 924. If we then take the 1365 down and divide it by that remainder 924, we get 441. We then take the 924 down, divide it by the 441, and we get 42. We then take the 441 down, divide it by 42, and we get 21. We take the 42 down, divide it by 21, and we get the answer 2, and the remainder is 0. So the highest common factor for this between these two numbers is 21. Okay, so that's an example of an algorithm. Now we can draw it out in this format here. So we could take our two numbers A and B. We can go through this process where we take A divided by B and we get our answer C. We then ask the question, is this value C 0? If it isn't, then we can go back up in here and we replace A with B, and we replace B with C, and we go back into this point here and again run through the A divided by B until eventually you get down to a point where the answer is in fact 0, and at that point there the final output will be B, which will be the highest common factor. Okay, now the question that was put by David Hilbert, who's a famous mathematician, was a question called the Entschuldigung problem, which loosely says, is there some general algorithm for solving all mathematical problems? And meaning really, can we have one master algorithm that will solve all mathematical problems? Now, a guy called Alan Turing comes along and he looks at that and he creates an imaginary machine. Now his machine looks like this. We just take the box there, we'll call it TM for Turing machine, and the Turing machine takes a ticker tape, so there's a ticker tape here, and it's an infinite piece of ticker tape. It sits in a box and that just goes on forever. Okay, and it acts on this ticker tape and it outputs it here, and again that end there just goes on forever. So if you think about this ticker tape just holding values of 0 and 1, so let's say the initial input's just here, 0, 1, 1, 0, 1, 0. Well, this machine here will take these values and they'll act on them in some manner, and the final output will be another set of values here. So in effect, this here just looks like an algorithm machine in the same sense that up here we take in the input, we go around the algorithm, and we get an output. Okay, now here's an example of the way he thought about it. If we think about an internal state of machine S and an input to the machine I, if we have a certain state and a certain input, then what we can do is we can either retain that at the same state or change the state, and we can retain the input at the value, or we can change that input. Now then we can then move one movement to either the right or the left, taking in the next value. Now, what is this internal state of the machine? Well, whenever we go to build the CPU, you'll see that we'll have registers, and we'll have a accumulator and a program counter. We'll have other things inside our machine that defines how the machine operates. So at any one point in time, you can take a snapshot in time and you can look to see exactly what is inside the machine at that point in time, or exactly what the state of the machine is at that point in time. Okay, so that's all we mean by an internal state. So let's go through these examples here. If the machine, for example, is in state 0 and it receives a 0 in input, then what we want to happen is it would remain in state 0, the input would remain at 0, and we would move one position to the right. If we were in state 0 and we received a 1 in input, we would then go to state 13, and the input would remain at state 1, and we would move one position to the left. If the state was in 1 and the input was a 0, then we would move to state 65, and we would change the input state from 0 to 1, and we would move the ticker tape to the right. If we're in state 1 and the input was 1, we would remain in state 1, the input would change to a 0, and we'd move one spot to the right. If we're in state 2 and the input was a 0, then we would go into state 0 and the input would change to a 1, we'd move one step to the right and then stop. So this is our algorithm, okay, and it's working on these inputs. Okay, so the contention is that this here is an algorithm in the same sense that this here is an algorithm. Okay, and the question then, we have a problem here in that we have to be able to represent not only the inputs in terms of zeros and ones, we also have to represent the algorithm. Okay, so not only does the data, but also the algorithm will be on this tape. So the question would be, how does this machine here know whether it's acting on an instruction or if it's acting on an input? Okay, so I've already drawn this out again on the next page. Okay, so let's say what we're going to use is what was termed in the book in contraction. Okay, so what we can do is we can represent 0, 1, 0. We'll define that as being 1. Okay, and 0, 0, we can define that as being 0. And 0, 1, 1, we can define that, 0, 1, 1, 0, sorry, we can define that as being 2. And 0, 1, 1, 1, 0, we can represent that as a 3. Okay, and obviously if we had 0, 1, 1, 1, 1, 0, we could define that as a 4. Okay, so on and so forth. So let's see how that would work. Let's say this is an input stream here. So there's the first line of it there, and there's the second line of it there. And if we were using this form of contraction, then we would know that these values here would be represented by what we got underneath. So the 0, 1, 0 would be a 1. Okay, the 0, 0 will give us a 0, 0, 0 will give us a 0, 0, 1, 0 will give us a 1, and then we have a 0 there and a 0, so that would be a 2. The 0, 1, 0 would be 1, and again that would be a 1 and a 2 and a 1, and the same throughout here. If you follow these along, for example, that pattern there would be a 0 and 4 1s and a 0, so that would be a 4. So if we take these here, this line and this line here, and we just write it out, then we'll end up with this line here. Okay, now it's all about interpretation and how we want to define things. So we can look at these numbers here. The 1001 would be the binary number 9, so that's 1, 2, 4, that's 8, and 1 is 9. We could then define 2 as a comma, because it's up to us how we define these other numbers, okay, the non-binary numbers. So we could represent that 2 as a comma, and then we would have the number 3, and then another comma, and then we'd have the number 1, 2, 4, okay, and then we'd have the number 3. Now how we define the number 3, that would be up to us, so we could have an instruction 3, okay, I just put in I3, I stands for instruction. Now that could be anything, it could be move left, move right, or stop, or whatever. There's whatever values, whatever instruction you want, okay. And we would have the number 3 here, and again an instruction 4 asking it to go and do something, and then a 0 followed by a comma. So now we've got not only the data but also the instructions all written out in the same line, okay. So if our machine received this data in, it would know how to interpret it, and it would read in this line here, and it would be able to act on the data and the instructions on this line. Okay, that's all for this little video. The next little video we'll come back and we'll look at the question, and I'll try and answer the question whether we can come up with a master algorithm that will answer all mathematical problems. Okay, thank you, and goodbye.